Hello everyone, my name is Bhargav Sri Venkatesh from IIT Bombay. I am one of the teaching assistants for this course, Quantum Information and Computing. Today we are going to discuss problems and solutions for this assignment 2. Before going into this assignment, I want to introduce some useful information which will be handy in this solving this assignment. So, qubit 0 is 1 0 and qubit 1 is 0 1. These are the standard notations we use for qubit 0 and qubit 1, and there are other notations like these things. Qubit plus is equal to 1 by square root 2 times qubit 0 plus qubit 1, and qubit minus is 1 by square root 2 times qubit 0 minus qubit 1. And now we will come to quantum gates or Pauli matrices. These sigma y equal to 0 minus I 0 and sigma z is equal to 1 0 0 minus 1. These are the basic information we need, and some more are: we denote a qubit in terms of theta and phi using block sphere, and theta is angle made with z axis and phi is angle made with x axis in equatorial plane. The previous Pauli matrices we mentioned can be seen as quantum gates, which we also denote as x, y, z, and the other important quantum gate which we use frequently is Hadamard gate, which we denote with h, and that is equal to 1 by square root 2 times 1 1 1 and minus 1. And it would be better if we remember some of the quantum states like 0 0, which is matrix product of which is similarly we can compute other states which would be better to remember, which will become handy in solving this assignment. I am writing the states here. And we will write corresponding matrices or vectors here. So, these are the useful information which will be handy in solving this assignment. So, now we go into the assignment and look at the first problem. The first problem says, which of the following operators represent a NOT operation? A NOT operation is also known as X gate, and we compute each of these options and see which of them is identical equal to NOT operation. So, question 1, and we are verifying option A says which is equal to 0 1 0 0. But what is a NOT gate? NOT gate is, which is same as X gate, 0 1 1 0, but the first option is equal to 0 1 0 0, so this option is not correct. So option B says it's equal to 0 1 times 1 0, which is equal to 0 0 1 0. We see that even this option is not correct. Option C we see that there are two terms here which we have computed already. So we just need to add the result of previous two options, which is indeed a NOT gate. Option D. It is 1 0 times 1 0 plus 0 1 times 0 1, which is equal to 1 0 0 0 plus 0 0 0 1, which is equal to 1 0 0 1, which is not correct. So the correct answer for this question is option C, which is equal to NOT gate. Now we look at question 2. We are provided with two states, qubit plus is 1 by square root 2 and qubit minus is 1 by root 2 0 minus 1. So the question asks what is the effect of X gate on these states. So on application of NOT gate on this quantum state, what would be the result? So we understand that on application of a NOT gate, qubit 0 transits to qubit 1 and qubit 1 transforms into qubit 0. So on application of a NOT gate, this qubit plus transforms to qubit 0 becomes qubit 1 and qubit 1 becomes qubit 0. So it's indeed qubit plus again. And when we apply NOT gate on qubit minus, we see that qubit 0 transforms to qubit 1 and qubit 1 transforms to qubit 0, which can be seen as negative of qubit minus. So the final answer is on application of NOT gate plus qubit doesn't transform, but a qubit minus transforms to negative of the same one. So the correct answer for this question is option B, which correctly shows the effect of X gate on these quantum states. So now we look at question 3, where we are provided with a quantum state and we are asked to find the resultant position on application of a NOT gate on this quantum state. The given quantum state is √3/2 times 0 plus half times qubit 1. So, what does this state transforms to on application of NOT gate? Qubit 0 becomes qubit 1 and qubit 1 becomes qubit 0. So, but the options doesn't contain this result directly. So, we need to verify whether each option is correct or not, and all the options are relating to the Bloch sphere. So, we look at positions of these quantum states on Bloch sphere. So, a quantum state is represented on Bloch sphere using theta and phi, which we compute using this form of quantum state. So, on comparing these qubit with this form, we see that in initial state cos theta by 2 is √3/2 and sin theta by 2 is half, and there is no complex component as a coefficient for the qubit 1. So, is 1. The final state cos theta by 2 is half. Cos theta by 2 is coefficient of qubit 0, and in the qubit 0 we have coefficient half. And even here we doesn't have any complex component. So, from these equations we get to see that theta by 2 is 30 degrees and phi is 0 degrees, and here theta by 2 is 60 degrees and phi is 0 degrees. So, phi is 0 degrees and theta is 60 degrees for the initial state. In the final state, theta is 120 degrees and phi is 0. So, to make sense of these options, let us locate these theta phi coordinates on a sphere. In the first state, initial state have theta equal to 60 degrees and phi equal to 0 degrees, and final state we have theta as 120 degrees and phi as 0 degrees. We know that theta is angle made by the state with z axis. So, we have this state making 60 degrees with z axis, and the angle made by this quantum state's projection on the x plane makes 0 degrees with x axis. So, its projection lies exactly on x axis. and final state, the angle made by the quantum state with z axis is 120 degrees. And the angle made by its projection onto the equatorial plane. Equatorial plane is the plane containing xy axis, is 0 degrees. So its projection is exactly on x axis. So what we see here is both these quantum states are in zx plane, because its projection onto the equatorial plane lies on x axis completely. So we can say that these two quantum states lying zx plane, one of them makes 60 degrees with z axis, another makes an angle 120 degrees with z axis. So as this angle is 60 degrees and angle between z axis and x axis 90 degrees, we see that angle made by the initial quantum state with x axis 30 degrees and the angle made by final state with x axis also 30 degrees. So as we have plotted these states on block sphere, now we go to the options. Option A says 60 degrees about x axis in the counterclockwise direction. So it's saying that the resultant position is obtained after rotating the initial state 60 degrees about x axis, but we obtain final state after rotating initial state by 180 degrees about x axis. So option A is incorrect, as well B. And option C says that we obtain final state after rotating 180 degrees about y axis, which is also incorrect. We obtain the final state after rotating the initial state by 180 degrees about x axis. And option D says a reflection in equatorial plane. Equatorial plane is plane which contains x and y axis, and we can clearly see that this both quantum states makes 30 degrees with the x axis on either sides. So option D is correct, which says the final state is a reflection of the initial state. So correct answer is option D. Now we look at the question 4. In question 4, we are given a circuit and input, and we are asked to find output provided by the circuit. And the input we are given is which can be written as 1 0. 1 is the first qubit and 0 is the second qubit, the input. And then it was shown a circuit H gate, Hadamard gate is applied on qubit 1. So the resultant state after applying H gate, the resultant state after applying H gate is because whenever we apply H gate on qubit 0, we obtain qubit 0 plus qubit 1 by square root 2, and whenever we apply H gate on qubit 1, we obtain 0 minus 1 by square root 2. So the resultant state is 0 0 minus qubit 0 0 minus qubit 1 0 divided by square root 2. And now we see that a condition NOT gate is applied, where control bit is first one and target bit is second one. So C0 gate is applied on state 0 0 minus qubit 1 0 divided by square root 2, which is the resultant we obtained after applying Hadamard gate. And the result of applying C0 gate is, as first qubit is control bit and the control bit is 0, second bit doesn't get altered, and in the next state, as the control bit is 1, the second qubit, which is 0, gets transformed to 1. And now X gate is applied on first qubit and Z gate applied on second qubit. We know that qubit 0 transforms to qubit 1 and qubit 1 transforms to qubit 0, because X is same as the NOT gate, and on application of Z gate on qubit 0, it doesn't get altered, but when Z gate is applied on qubit 1, we get a negative coefficient. So based on these results, X gate on first qubit and Z gate on second qubit, we obtain, as we have qubit 0, it will get transformed to qubit 1 as X gate is applied, and qubit 0 transforms to qubit 0 on application of Z gate, so it stays 0, and the 1 qubit transforms to 0 as X gate is applied, and qubit 1, which is second qubit, transforms to minus 1. So we obtain 1 0 plus qubit 0 1 divided by square root 2 as answer. So which is so we obtain answer qubit 1 0 plus qubit 0 1 divided by square root 2 as output state, which is option B.